A warm welcome to part 1 of the lecture on limits. For the past few lectures, we have been learning about functions. Today, we move to a concept of paramount importance in analysis, namely the limit of a function. Before we move forward, let me motivate you as to why limits are important. Well, the concept of limit is ubiquitous in analysis. It is all prevailing. One of the chief goals of analysis is to approximate not so good or rough functions with much better or well-behaved functions. In this context, an important theorem which comes to my mind is that of the Weierstrass approximation theorem, which basically is a theorem of approximating continuous functions on a closed interval a comma b by means of polynomials. However, in this course we will not go deep into learning that theorem as it is beyond the scope of our discussion. Having said that, an important question immediately arises, which is, what is meant by such an approximation? Any route of understanding this approximation must pass through the gates of limit. The most important concepts in analysis, like continuity and differentiability of a function at a point, are defined in terms of a limit. The integral integration a to b fx dx, whenever it exists, where f is a bounded function, is also defined in terms of a limit. Not only that, the very question of existence of this integral is based on two limits being equal or not. If they are equal, this integral is said to exist and its value is equal to the common value of those two equal limits. And if those two limits are not equal, then this integral is said not to exist. We will say a bit more about this when we come to integration. Many standard functions, like the exponential function, are the limits of their power series expansion. Limits play an indispensable role in understanding the notion of convergence and divergence of a sequence or series of real and complex numbers or real and complex valued functions. The pivotal role of limit in analysis cannot be overemphasized. It is therefore essential for us to deeply understand what the limit of a function actually means. With this motivation, let us proceed to formally introduce the notion of a limit. Our primary objective is to gain a deep understanding of the meaning of the expression limit extending to a fx is equal to L. Following this, we will discuss some important properties of limits and finally use these properties to develop techniques to evaluate certain limits. To achieve our objective, we will, however, first introduce the notion of a sequence and discuss what is known as the limit of a sequence. The reason for doing this is twofold. First, the notion of limit is much easily appreciated in the context of sequences, while retaining the quintessential matter needed to understand the expression limit extending to a fx is equal to L. Secondly, the expression limit extending to a fx is equal to L is intimately related to the convergence of a particular sequence. There exists a strong result which asserts that limit extending to a fx is equal to L if and only if a particular sequence converges to L. We will state but not prove this result more formally later. Now let us define a sequence. A sequence is a function from the set of natural numbers n to the set of real numbers r or complex numbers c. F from n to r or c. Depending upon whether it takes values in r or c, it is called a real sequence or a complex sequence. In the context of sequence, the letter f is rarely used, and x or y or z or s are generally preferred. So x from n to r or c is generally used for a sequence. X of 1, x of 2, x of 3, etc. are called the terms of the sequence and are conveniently denoted by x1, x2, x3, etc. The general term or the nth term is denoted by xn. The whole sequence is conveniently expressed as xn, where n belongs to the set of natural numbers. The sequence xn is different from the set of its image points. For the sake of avoiding confusion, we will denote the set of image points of the sequence xn by using the curly brackets xn, where n belongs to the set of natural numbers. As an example, consider the sequence minus 1 to the power n. The terms of the sequence are minus 1, 1, minus 1, 1 and so on. So it keeps oscillating between minus 1 and 1. But the set of its image points is only minus 1 and 1 because the sequence takes only two values, namely 1 and minus 1. Let us see some other popular examples of sequences. Harmonic sequence 1 by n. So terms of the sequence are 1, 1 by 2, 1 by 3, 1 by 4 and so on. The complex harmonic sequence, which is I to the power n by n, where n belongs to the set of natural numbers. The terms of the sequence are I minus 1 by 2 minus I by 3, 1 by 4 and so on. The geometric sequence, the general term of which is given by a into r to the power n, where n is greater than or equal to 0. The terms of the sequence are a, ar square, ar cube and so on. The arithmetic sequence a plus nd, where n is greater than or equal to 0. The terms of the sequence are a plus d, a plus 2d and so on. Sometimes a sequence can also be defined by specifying the first few terms and then defining the remaining terms by means of the preceding ones. This method of definition is called the recursive definition. The geometric sequence can be specified recursively as follows. A naught is equal to a and ak is equal to ak minus 1 into r for all k greater than or equal to 1. Similarly, the arithmetic sequence can be expressed as a naught is equal to a and ak minus 1 is equal to d for all k greater than or equal to 1. The Fibonacci sequence. It is given by a naught equal to a1 equal to 1. This is specified. And then ak is equal to ak minus 1 plus ak minus 2, where k is greater than or equal to 2. We have seen some examples of sequences. Let us now proceed to formally introduce the notion of limit of a sequence. But before we give the formal definition, let us consider an example which will aid us in digesting the definition, which is somewhat technical. Consider the sequence xn equal to minus 1 to the power n by n for all n belonging to the set of natural numbers. We wish to investigate the behavior of this sequence for larger and larger values of n. So x1 is equal to minus 1, x2 is equal to 2, x3 equal to minus 3, x4 equal to 1 by 4 and so on. So if you plot these terms on the number line, you get this. So x1 is equal to minus 1, x2 is equal to 1 by 2, x3 is equal to minus 1 by 3, x4 is equal to 1 by 4 and so on. An important observation is, as the value of n increases, the terms of the sequence minus 1 to the power n by n get closer and closer to 0. The phrases larger and larger and closer, although intuitive, are qualitative and not quantitative. We wish to quantify them and make them mathematically precise. For this purpose, we must introduce the concept of a neighborhood. The epsilon neighborhood of a point A belonging to R. It is defined as an open interval I centered at A and having length 2 epsilon. So let us see this on the number line. A is a point belonging to R. So this epsilon neighborhood of the point A is the open interval I, which is of length 2 epsilon, and the center is at A. So it is denoted by n subscript epsilon A or B A comma epsilon, and it is the set X belonging to R such that mod of X minus A is less than epsilon. It is not the most general definition of a neighborhood, but suffices for our purpose. Similarly, an epsilon neighborhood of a point Z naught belonging to C is defined as an open disk centered at Z naught and having radius epsilon. The term open signifies that the boundary of the disk is excluded. So n epsilon Z naught is basically the set Z belonging to C such that mod of Z minus Z naught is less than epsilon. By means of these neighborhoods, we can quantify the phrase closer and closer. The degree of closeness or proximity to A or Z naught is captured by epsilon. Smaller the value of epsilon, closer we are to A or Z naught. Neighborhood of a point A is the set of points which are close to A. Exactly how close they are is specified by the value of epsilon. Let us make one more definition, which is the neighborhood of infinity. Let m greater than 0 be a real number. A neighborhood of infinity is the set X belonging to R such that X is greater than m. A neighborhood of infinity precisely captures the phrase larger and larger. Greater the value of m, larger is the magnitude of X lying in the corresponding neighborhood of infinity. Now, having defined the notion of a neighborhood, we are now well equipped to introduce the formal definition of the limit of a sequence. Let xn be a sequence and let L be a number. Xn is said to converge to L, or equivalently L is the limit of the sequence xn if for any given epsilon greater than 0, there exists a natural number n such that mod of xn minus L is less than epsilon for all n greater than capital N. The definition basically tells that xn converges to L if and only if the terms of the sequence xn lie in an arbitrarily small neighborhood of L for larger and larger values of n. Let us confirm using our definition that the sequence minus 1 to the power n by n converges to 0. Let epsilon greater than 0 be given. Let capital N belonging to the set of natural numbers be such that n is greater than 1 by epsilon. If small n is greater than capital N, then mod of minus 1 to the power n by n minus 0 is equal to 1 by n, and since we have taken small n greater than capital N, therefore 1 by small n is less than 1 by capital N. But 1 by capital N is smaller than epsilon. So we conclude that mod of minus 1 to the power n by n is less than epsilon for all n greater than capital N. Thus, according to our definition, minus 1 to the power n by n converges to 0 as n goes to infinity. I will stop at this point. In the next lecture, we will see quite a few more examples of converging sequences and then move on to study some properties of limits. Thank you.